Hi, welcome to StatStuff. I'm Matt Hansen. This lesson is part of an extended series on hypothesis testing in the analyze phase. In this lesson, I'll introduce you to the types of tests that measure relationship between factors. This lesson doesn't have any critical prerequisites for the concepts that I'll discuss, but I still recommend that you review the other lessons on hypothesis testing if you haven't already done that. But for now, let's review again why we even need hypothesis testing.
Well, we need hypothesis testing because, remember, our goal for the project is to resolve the problem by first building a transfer function. We don't want to just alleviate the symptoms that we're seeing, but we want to get to the root cause. You may recall my example of my daughter Hannah. We don't want to just alleviate the arthritis pain that she was feeling in her leg, but we want to heal the root cause, which was the strep throat. So if we don't know what the root cause is, then that means we need to build a transfer function to figure that out. By building the transfer function, we can know what changes, that is, what improvements that we need to make that should fix that root cause. Now, if you recall, the transfer function is defined as y equals f of x. That is, the output response of y is a function of one or more input x's. It's part of the IPO flow model, again, that we described before in the IPO flow model, where we have an input that leads to a process and an output. Well, the y refers to that output. The process piece refers to the function that's applied to an x, the x being the inputs that are part of it. So it's really expressed in the IPO flow model to an equation. Now, how does this transfer function fit with hypothesis testing? Well, hypothesis testing tells us which of those x's, which of those inputs that we're looking at, are independently influencing the y, the output metric. When we reject a null hypothesis, we're building evidence proving which x's are guilty of driving the y. And what we'll do at the end is we'll compile all the evidence in the improve phase of DMAIC, and that's when we'll begin to fix those root causes or come up with a plan that's going to fix those root causes. Now that we know from the hypothesis testing which of the x's are the most critical x's that have the most influence and where we need to make the biggest changes that are going to affect our output y.
Alright, now we'll look again at the familiar chart for finding the right statistical test. But this time I'll show you how relationship types of tests are very different from the different types of tests that we've been looking at so far.
Relationship tests are very different when we consider the perspective that they take when they look at statistical tests. So the kind of perspective they take really depends on the source of the distribution that we're looking at and what we're trying to test for, that is, whether we're looking at differences or similarities. So when we look again at the drill down that we've used before to find the right statistical test, what we've seen on here so far up to this point are the lessons that refer to these types of statistical tests. And for these tests, these are really looking for differences within similar groups or distributions. That is, when we compare similar groups, like we're comparing the performance between two people or two locations or two call centers or whatever it is, they're comparing one thing with another, they're things that are similar to each other, we're looking to see if there's a difference between them. And these kinds of tests will look and tell us if there is a statistical difference between the things that we're comparing. Well, relationship tests are a little bit different than that. What they do is kind of the opposite. They're taking different groups, different distributions, and they're looking for similarities between them. They're doing a comparison between those different groups to see if there is any similarity between these things that seem to be very separate or different from each other. So it's important just to understand the difference in how these types of tests are looking at. Again, the ones we looked at before are looking for differences among similar groups, and the relationship tests we'll be looking at next are ones that look for similarities across different groups or distributions.
Okay, now let me introduce you to the concept of correlation and how we measure it.
Well, correlation is a measure of linear association between two independent continuous values that we're looking at. That is, like two numerical values, to see if there is a linear association between those values. More specifically, it's referring to how much we can explain as a linear relationship or linear association between those two values that we're comparing. So what is a correlation coefficient, or what's also known as a Pearson correlation? Well, that's a way of measuring the strength of the correlation between the two factors or those two continuous values that you're comparing. So it does this by plotting those coordinates for those factors, and it's trying to draw a line or fit a line between those factors, and as good as a line is in how it can draw determines how strong it is. So the distance that each of those different factors or observations are from the line that it's trying to fit, that distance represents the errors or residuals we'll be looking at later. That helps determine how strong the correlation is. The correlation coefficient, the result that results from that, will fall on a scale between -1 and +1, or the same thing as saying like a -100% all the way up to a +100%. Now R is what we refer to as the sample correlation coefficient. And the Greek letter that looks like a P, that's actually called rho, that is referring to the population correlation coefficient. So let's look at a few examples of how we can compare the extreme differences between the type of results you might see as a correlation coefficient. First, what we'll look here on the left this is an example if we had an R value, which is like the sample correlation coefficient, of -1, the lowest possible extreme, or like a -100%. What this is basically saying is that 100% of the data points can be explained as a negative, or that is an inverse relationship. That is, as one factor goes up, the other factor has an immediate relationship of going down. So they're inverse from each other. One goes up, the other one automatically goes down. And when we say this is the extreme, they all fit on the line, and this is the extreme type of example where you have a -100% or -1.0 as your R value. Now, in between that, we would see that there is an R value of 0, which is basically something like this, where you have all your data points scattered across the scale. And the line that it tries to fit in here just doesn't seem to fit across any of those observations. So in this case, we would say the R value is 0 or 0%, or we're also saying that 0% of the data points can be explained through a relationship of those two factors that you're comparing. So there seems to be no correlation whatsoever between those factors. As one goes up, the other one could go down or could go up, and there really is no relationship between them. The other opposite extreme is to look at R is equal to a +1 or +100%. This is where we're saying that 100% of the data points can be explained as a positive relationship. That is, as one goes up, the other one does go up at an equal level, and they're correlated with each other. So again, as one is going up, the other one's going up at the same rate. As one is going down, the other one is also going down at the same rate. So that's total opposite of what we looked at before, where there's the inverse relationship. One goes up, then the other goes down. In this example, they're going up or down at the same rate, all again related with each other. These are the examples of the three extremes that you might see as a correlation coefficient, but it's very rare that you would actually see it like this. But this is just to illustrate for you the type of extremes that you might be able to see. But realistically, we'll find some R values when we compare the two values and we're trying to come up with a correlation coefficient. Most often they'll fall somewhere less than this extreme of -1 and less than this extreme of +1.
Now we'll look at a guideline to help you decipher how strong or weak a correlation is.
So how do you know how to determine the strength of a correlation that you're looking at between two factors? Well, generally the further the correlation, or that R value, is away from 0, the stronger it is. So that is, the closer to a -1 or the closer to a +1 that your R value is, then the stronger that relationship. But there's not a perfect threshold for determining whether a correlation is weak or strong. Some folks have recommended certain thresholds that have been proposed that would say that this is where you determine whether a correlation is strong, when it's at least this threshold of 75% or 50% or something more extreme. But I would not really recommend that. I think it really depends on the factors of what you're using and the kind of relation that you'd expect between the things that you're comparing. So I would first ask yourself, do you expect a relationship to exist between the two factors that you're comparing? If you do expect a relationship between them, then I would use the part of the scale that I'm about to show you that is more strict or more conservative. However, if you wouldn't have expected a relationship between the factors, you're using two factors that are very obscure from each other and you would have never expected a relationship, then I would recommend using the other part of the scale that I'm about to show you, and that's where it's a little bit more liberal and lenient in the way that it approaches it. So here's what the scale might look like. Well, this is where we have the extreme on the left-hand side of a -1, all the way going up to a +1, which could again be a -100% or a +100%. Right in the middle is 0, where we would say there's no relationship. So in these two examples here, each row represents a guide that you might use for determining the strength of relationship. In either case, the closer that each of these are to the extremes, that is, the further away they are from the middle point, from 0, then the stronger those relationships are. So again, when they go further to the left, to the -1, it's a stronger inverse relationship. When they go further to the right, it's a stronger positive relationship, again, where they're going together up and down at the same rate. Now, what I mentioned before about whether you can't have a certain threshold, what I mean is, I'd first ask yourself again, do you expect a relationship between the factors? If you do expect a relationship, then you might use this upper row as a guide to determine where the strong, moderate, or weak level is in what you call your relationship. So that is, if you do expect a relationship to exist between the factors, then probably something greater than 75%, if it's a positive like this, you might call it strong. Otherwise, if it comes between about 50% and 75%, you might call it moderate, and somewhere between 25 and 50%, you might call it weak. If it's something less than 25%, whether you're on the negative or the positive side of the scale, you might just say there really is no relationship, because you're expecting there to be one. The factors you're comparing, you would have expected some type of relationship to exist. However, again, if you would not expect a relationship to exist, this is where I recommend using this lower row, which is a little more liberal and lenient in how you approach this type of interpretation of the strength of the correlation. So where you say you don't expect any relationship, the values you're comparing are obscure from each other, then I would say anything above 50% you probably can consider to be strong. Anything between 25 and 50 you might call moderate, and if it's less than 25 or above 0, when you see something there, then you might say, well, there's some kind of relationship, although it might be very weak. Now, this is really critical to understand, again, the differences between them, because I don't think you can just automatically say, here's the immediate threshold and where you draw the line. If something falls at 49%, you know you're so close to moderate. If you're expecting a relationship, then you might as well just call it moderate. It's not a big deal. It's not like you have to use these as a hard and fast rule. In either case, this is just a general guide for how you might interpret it, but I would never recommend anyone use this as the formal rule for defining where the threshold is, but let it just be a guide. Again, if you don't expect a relationship between something and you're seeing it at maybe at maybe 48 or 49%, you might as well call it strong. You're really close to it. You're on the upper end of moderate, so you can call it strong. No one's going to shoot you. It's not a big deal. The point is, though, that this might be a guide so you can figure out what to use. An example I like to think of is there was a project I was running. I was using a comparison of how one surveying company was surveying the results, and the results that were coming back from the survey, I was running a correlation with the actual survey rate, how much they were actually surveying, the size of the sample considering with the number of total volume in the population. So I would have expected no relationship between them. The results came back at about 45% of a relationship, but I expected no relationship. In that case, it was on the upper end of moderate. It was enough for me to realize that I needed to take some action, and sure enough, when exploring it, I found in that particular example, the actual approach for the survey was appropriate, but it was our interpretation of how we're interpreting those results from the surveying company were very wrong. And this is really what enlightened us about that, because we saw there was more of a relationship than we would have ever expected. So it really changed the way we think about and approach the survey results provided by that company. So it's important just in that example to show that it's okay if you have something that's might seem like relatively small in a correlation. Again, if you don't expect a relationship, that actually could be something strong.
All right, now let me introduce you to the concept of regression and what it measures.
Well, to define a regression, first we might be reminded how a correlation, or that R value, is measuring the linear association between two variables. Well, a regression builds an equation, or what we call a model, describing the nature of that relationship between the two variables that you're comparing. So an equation will generally look something like this, where you have the output Y response is equal to a constant value plus the coefficient multiplied times the X predictor. So in this example, a constant is just some stationary value that it gives you in the results that you add to this multiplier, where you have some X factor you're comparing, which will be one of the variables you're using in your equation, as well as the Y response is the other variable that you're looking at. So the result of the equation is going to tell you, here's the constant that you can use in building your equation, and here's the coefficient you can use as your multiplier for the X predictor. So it's important to remember that the coefficient is merely a multiplier of your X predictor. So it's just a factor that multiplied in front of your X. So when you create the regression, it creates for you this type of equation. Now, with that equation, you could do several things. And we'll get to that in just a second, but the quality of the regression is measured by squaring the correlation coefficient, or what's called the R squared value. So it measures the proportion of variation explained by the regression model. So what is it that we can do with this regression or having this type of equation? Well, we can build the equation or the model that's similar to the transfer function. So that will allow us to explore the existence of the relationship between two or more variables that we're looking at. We could also use it to forecast or predict outcomes. So with this type of equation, we can plug in other variables into this, that we can use that to predict future results or do some additional forecasting. As well, it's a way for us to validate the equation. We can determine how accurate the equation's prediction was. And then finally, we can determine driving factors. So we can determine what are the key factors that could influence our output Y or response the most.
There are a couple critical risks associated with relationship type of tests. Let's start with the first one that deals with the sample size that you're analyzing.
One of the first big risks that we need to consider is about dealing with the sample size. Remember, we can draw a linear association or correlation when we just have 2 data points. All it takes is 2 data points to draw a line. So we could technically have something like this as our value that we're comparing for the correlation coefficient. In this example, the R squared or the R value is going to be 100%. But is this really acceptable to even have it like that? Well, obviously it wouldn't be. So at what point do you know if you have enough data points that you can trust your R squared value? Well, in Minitab, it will generally calculate for us an R squared adjusted value, and that will usually be one of the outputs that comes from these types of regression tests. So you look for the R squared adjusted value, which accounts for the number of terms and the data points in the regression model. So in this example, it might return technically like an R squared of 100%, but the R squared adjusted will be far smaller because it's accounting for there only being 2 data points. But the more data points you add to this, then the closer your R squared adjusted will get to the R squared value. So if there are too few data points, your R squared adjusted will generally be smaller, and if there are enough data points, the R squared adjusted will be closer to, but it'll never exceed, the R squared value. So it's helpful as a rule of thumb, just use the R squared adjusted for every test that you're using, especially if you have that available like with the Minitab, and that way you can use that just to be sure that you've accounted for enough data points in the analysis that you're running.
Alright, now let's look at the other critical risk that deals with interpreting test results as correlation versus causation.
Well, again, the other big risk that we need to consider is that just because you could draw a relationship between factors doesn't mean that one factor is actually causing or driving the other. That goes back to the issue of correlation versus causation. So a relationship may exist between variables simply because they're actually both dependent on or maybe influenced by some other independent variable. So let's look at this example. Let's say you've got sharks and ice cream. Well, we could plot out a chart that shows the shark attacks versus ice cream sales. Now, if we didn't know any better in looking at this, it looks like there's a relationship here, a positive relationship, where as shark attacks increase, ice cream sales are also increasing about the same rate. So, is there a relationship between shark attacks and ice cream sales? Well, that would sound kind of crazy. So if we didn't know any better and we didn't question that, we might be inclined to stop the ice cream sales so that way we can prevent shark attacks. Well, again, that assumes causation between them. So since it doesn't make sense, we should ask ourselves, is there another independent factor in which these 2 variables, shark attacks and ice cream sales, are really dependent? Well, in this case, it probably is summertime, where in summertime you tend to have higher ice cream sales, and you also, because it's summertime, more people are underwater and you're more susceptible to shark attacks. So there's actually some other factor that affects both of these. So shark attacks and ice cream sales are actually both dependent on another factor like summertime. So rather than seeing just these 2 factors in comparison to each other, it doesn't mean that one is actually causing the other. So when you have something like this, always make sure the relationship that you're comparing between the variables is logical. It has to make sense. If there really is a causation between the variables that you're comparing, you should be able to test it in additional ways so that you can validate that cause. So for example, if I was running between these 2 values and I see this relationship, I should be able to also run it in many different ways as well, such as other parts of the year or other ways of how I might be able to break down the data according to other factors or groups, and I should be able to see that relationship exist. Well, normally we wouldn't test for things like this. But other factors, let's say you have 2 metrics within your organization, you're comparing between each other, and you see some relationship between them. Well, you don't know necessarily if the relationship that you're seeing is, again, dependent on some other independent factor that you just didn't account for. So if the relationship truly exists between those factors, and you're seeing that and it's just kind of odd to you, another way to test it is just take those factors and break it down in different ways. So if you're reporting it at a weekly level, well then break it down to a daily level, or also show it at a monthly level. If you're seeing that same relationship exist at those different levels like that, or even if you were to break it into different groups, depending on what you're looking at, if it's some results that you can break down between different regions of the country or by different operations centers or production lines or different things like that, different product lines that you might have. Whatever way, if there truly was a relationship between the metrics you're comparing, you should be able to break it down in different ways and explore it and see if that relationship exists. If it doesn't exist, as you continue to break it down and look at it from different angles and perspectives, then it probably is not causation, and you should not take action assuming it is. However, if you do see that it does seem to be consistent no matter what way you look at it, the relationship does exist, then you probably can trust maybe there is causation after all, and you might be able to take appropriate action.
All right, before we close this lesson, let's discuss how we can apply some of these concepts in a practical way.
I'd like you to refer back to the critical metrics that you've been using as part of this hypothesis testing, and then for each one of the ones that are using continuous values, ask yourself the following. First, which sets of those factors would you expect there to be some correlation between them, and why would you expect a relationship like that? What would you expect the correlation percent or the correlation coefficient to be? And what could it mean if you actually found that there was much less or maybe no correlation as you had expected? And which sets of the factors would you expect there to be no relationship at all, and why would you expect that? And what could it mean if you did find a correlation? So as you consider these types of things, it's important to try to consider this ahead of time before you actually run the statistical test.
Well, that wraps up this lesson. Check out StatStuff.com for many more resources that can help you achieve powerful results. I'm Matt Hansen. Thanks for watching.